Yeah, we're back to the hands-on now. Yeah, we have time for this. So go to the MPI directory this time. So in that Prace folder, just take a little look over this MPI blocking.c. You don't have to pay a lot of attention to exactly what it's doing. It's an MPI code. There's some headers in there to give you some information about what each piece is doing. The piece you're interested in is the communication section further down. You should be able to just compile it and run it. It requires some other arguments different to before. Just have a look, see what it's doing, see what you think it's doing, compile it and run it. Gusty, what time is the coffee break?
Whenever you want, actually.
If you want to, what would you prefer? We can take a break now and then come back to this after the break, or we can do it and it won't take so long. The MPI section wasn't really intended to be too long.
I just need to tell the guys to prepare the coffee break.
So this whole MPI thing will take about another 20 minutes or a half hour or so, 20 minutes maybe, something like that. So how did it go? Did you get to compile it, run it? Any problems?
Yeah, a couple of warnings.
Yeah, don't worry about the warnings. Yeah. Yeah, so there's a description inside saying what it's actually doing. I don't know if you got to read it. So, just to give you an idea about some of the problems, so there's a couple of problems in this routine, or performance-related problems. Let's actually, I'll run it, why not? Okay. What did I suggest? 204. So I just ran it. This one actually computes the communication time for you a little bit. So it tells you it spent 6 seconds communicating. If we go to our job digest from the LWM, we can see it only ran for 7 seconds, so it basically spends all its time communicating. We can see, and you can actually see that in the figures. So actually it spent, in MPI, it spent 98% of its time in there. Mostly in peer-to-peer calls. Yeah, probably almost all, because I know it's only peer-to-peer calls.
Where this output is coming from?
This one, this job digest, it comes from this tool I talked about earlier on, LWM2. So basically what it does is it interferes. So when the code runs, it needs to link back to the MPI library. This application steps in the middle and captures that call, and then forwards it on. So it basically steps in the middle so that it can measure some stuff, very lightweight, and then so it's able to see these calls and how much information is being passed around and things like that.
But You put this.
It's inside the job script. If you look in the job script, you'll see how I set it up inside there. All right. And so basically, it gives you some information about the MPI as well. I haven't really looked at this information so much, so I can't really tell you about how you would use that so much. But the file I/O, there shouldn't really be any because it doesn't actually open out any files. Effective threads doesn't really mean anything here because we don't have threads. We just have our MPI processes. It has some performance information as well. Again, don't really care too much about this because we know it's not doing a lot of work. So the thing is, it spends a lot of time in MPI, and we want to fix that, right? So it's spending 99% of its time in MPI and not doing any actual real work. So we should take a little look inside and see what the particular problems are. There's kind of two obvious ones. One of them I created, and one of them was originally there with the idea of it. You can tell a bit by the name that what the problem might be. It's called blocking, all right? So there's blocking in the name there somewhere. So that's basically what we're going to look at. So we'll look at this communication section. The timing is used as the MPI timing. So basically, it starts a clock, and at the end, it has a barrier, and then it finishes the clock, right? So the reason I had the barrier is because I have this wall time. Probably, I don't know if you've taken a good look, but you can see there's a problem with this barrier. Its location. So really, I only need the barrier before I did the wall time. But I did a little mistake, or a deliberate mistake, and I put it this inside this semicolon. So what actually happens?
You call the barrier many times.
Many times, right? I'm calling this barrier. So I can probably improve the execution time a lot just by moving this MPI barrier to where I actually needed it, which was before I called the wall time. Right? That's one of the things you can try. Give it a go. Just move that out and see how does it change your performance. But then the other one, the one that I kind of wanted to talk about a little bit more, is to do with the actual communication that happens. And I kind of thought I don't know if this will work, but we can try it, that the easiest way to explain the problem is for people to become processors, right? So if you have a problem with C, then, okay, it might be hard for you. It won't be hard, right? So you're one process, here's your information. You're rank 0, you're rank 1, you're rank 2, you're rank 3, okay? So, all right? So you're all executing your own piece of code. You know what your task ID, okay, in this case it's called task ID. Okay, so we're coming to the first cycle, all right? We're looking at rank 0, that's you now this time. So you're rank 0. So the piece of code that you're interested in is here, right? Because you're rank 0, right? You're rank 1. So basically, if you're 0, you're doing this piece. If you're n task minus 1, which would be you over here, the last one, this is your piece over here, right? And if you're anyone else, which is you two guys, you're in this region here, okay? So on the first cycle, right, everybody comes to the same point. We're all starting into our own piece of code. So what happens, right? 0, you're on the receive. What does that mean? Nobody sent you a message yet, so you wait, all right? So what do?
I go to else. I'm the else.
You're the else down here. You wait. What do? You're also here. So you wait.
I like him.
Yeah, so you wait, right? You're all the same. So we got 3 people waiting. And what do you do over here? You send, right? So now we come to the next loop. We take your message off of you. Right? So this is your message. Right? So this is your piece of information. You're sending it over. You can see you're sending it over to wherever it is. 0, right? This is you, right? So now he sent a message over to you, and the next thing, and now we're on to the next cycle, okay? So in this case now, you're stuck back to waiting, right? So you've moved on, you sent your message, and now you're receiving, okay? So now you wait, right? What do? On this cycle,
I do mine.
you receive, so you get your information, right? What do? Nothing, you wait, right? You're still waiting. She hasn't said, and you wait, right? Okay, so now we're waiting again, and you're still waiting over here. We go to the next round. You have your information,
Yes.
now you can send it, right? She sends it to you,
Thank you.
and you receive. What do?
I get it and send it.
No, you haven't got it yet. You have to wait.
Okay.
You have to wait. And what do? Wait. Right? Right? And now and you're waiting now, right? So now we go to the next round. You've sent, so this time he can receive.
I first measure the time. I mean.
Oh yeah, okay, but basically the idea is with the messages, you can see what's happened, right? We've serialized the whole thing. Everybody has to wait all the time. Everybody is wait. One guy sends a message, we wait. Everybody waits. We send a message, we all wait, and so on, right? So we've serialized everything, right? It's turned into a. It's really bad. Our performance is really bad. Why is that? Because we have all these peer-to-peer things. So this is back to the thing we did earlier, where we try and improve it, right? So what are the possibilities for improving it? So we can see basically what we had is the serialization, right? So if you look at the code and think about what each rank is doing individually, you see that actually they spend an awful lot of time waiting because of the way the code is set up, right? So we have a big problem because we've introduced this serialization of the whole thing where we send a message, receive a message, and then do that sequence by sequence, okay? So the solutions are, we can think about using non-blocking routines. That's the solution that's in the exercises. Or we can use a buffered send, which is another routine. I don't know if you talked about it the other day. We're not going to look into that. The other option is to use an MPI send receive, right? So rather than split it into two calls where you have a receive and sends, this type of communication where we want to do sends and receives to a number of processors happens a lot, right? So they have a special call that takes care of this kind of scenario, and it's an MPI send receive. Okay, so the next part that are hands-on then is to look at this MPI blocking.c, to focus on this particular area. We looked at the issues already, we know what they are. One of them is the MPI barrier that needs to be moved, and the other one then is the fact that we've serialized all the message passing. So solve them, right? One of them is easy, you just move a line of code. The other one, you need to use something else. I want you to use MPI send receive because the buffered one is in the solution already, so I'd like you to try and use the send receive instead. I'm not going to give you all the parameters of MPI send receive. If you're on your own, the easy solution is just to Google it, right? Stick the function into Google, it'll tell you all the parameters inside. You already have the parameters of the send and the parameters of the receive. It's in the code already. So basically all the information you need is already there. You just need to put the arguments in the right places for the send receive. And that's it. Make a copy of the original if you want to keep the original. It doesn't really matter. And then that's it. Give it a go. Run it again. See how your performance improves.
I will send it back
A question.
Yeah.
In this case, these are nodes or cores.
Course. This is course, yeah.
So they basically do not. They have access to the same memory.
No, because it's MPI.
No. Okay, so.
I mean, they have access to the same memory, but it's distinct memory spaces, right? So not directly, they don't. I mean, the MPI implementation might be clever, right? But you can't assume that it's clever.
Okay. So if at the same time some other process is run on the same node, what happens to the memory?
The only place that will affect you is, I mean, when you allocate a piece of memory, it's protected, right? Typically, you can do clever things to implement that, but affect that, but it's protected, right? So it's your piece of memory. So the main memory doesn't affect it. I mean, other processes running, they have their piece of memory, you have yours. Where it can affect you is in the cache stuff. The caches obviously are shared, right? The main memory, you have your piece there, they have theirs. But when you start loading the cache lines, then it's a shared space, and so sometimes if somebody else is doing something that's memory intensive, then they can affect your performance because the caches don't work the way they're supposed to, because somebody else is getting in there ahead of you and things like that. So, but in general, yeah, it should. So in this case, this is why clusters like this are kind of useful, because you get a whole node to yourself. So you can only affect yourself, right? I mean, okay, there are some processes running in the background, but they're meant to be very lightweight, right?
Well, I will ask you more after the...
Yeah. Yeah.
There used to be something called persistent communication, which we used, in MPI. You know that? You do an opening of a channel and then you don't have to start a time using it.
I don't know about it, to be honest. Did you do it the other day, was it? Or?
Yeah, I did. I used it.
I don't know. I actually don't do so much MPI coding anymore myself,
okay.
Right? So I'm doing some simple stuff here.
That was something that you could use here, maybe.
I find it hard to believe it doesn't have any. It still has to have you still have network latency. I think.
It's plain MPI, you know. It's something.
What's it called? What's it called?
I can look at it.
Yeah, I haven't even heard of it before, to be honest. But. Yep.
Different tags.
No. So the reason for no is because you have to think about the different memory spaces. So, well, yeah, maybe. In this case they won't, right? Because you only go from one side to the other side. So there's no possible way that they could mix it up, right? Because it's only from this guy, it's only going there. If they were receiving multiple messages, maybe. But actually, the tag stuff, I can't remember exactly how that works, but I think it's not such a big...
Because I had once this situation, and
yeah?
only by sending tag number...
Yeah, it could be, yeah, it could be.
Because they were confused with which message.
Yeah. Yeah, I mean, in this case, or in the case particular here, you wouldn't have had that problem because it's a blocking send-receive, right? In a non-blocking case where you have multiple messages potentially coming in, yeah, okay, you would, yeah. So how do we go? Did anyone manage to get it to compile the MPI send-receive?
Previous exercise.
Yeah.
About this OpenMP.
Yeah.
How does it know to divide to threads?
Because you told it here. So you told it. So.
Told it by.
So you told it here that it was a parallel region and it has a private seed, right? And then the next step you told it, this is my pragma. It's a parallel for, right? So it knows that the next for loop it sees, it's going to try and parallelize that for loop.
Always the next loop?
So basically it's going to be the next line, yeah, in this one, because you're telling it that this is to parallelize this for loop.
So it's like takes the DMX, it's divided by the number of threads?
Actually, what it actually does depends on the implementation. So
of the compiler?
Of the compiler, yeah. So in this case, it could do a number of things, right? It could do one element for I, one thread. Or it could say, you do the first 8, the next guy does the next 8, or it could say, it depends, the chunk size and everything, it depends on the compiler. You can actually tell it exactly what to do if you want. You can say, divide it up one by one. There are a number of commands, extra commands you could give to tell it exactly what you wanted to do. Here I gave it the default behavior. And that could actually potentially run into problems. Because if, so let me see, where would it have been a problem? No, it probably wouldn't have been a problem. It could be a problem in a particular set of dimensions for it might have been a problem, but in this case it typically wouldn't have been a problem. But basically, what actually happens depends on the compiler, how it cuts it up.
And then it sums it up, like because of doing reduction, right?
Because I tell it that I want a reduction, and so it knows that this has to be protected a little bit. So it's specific to each thread. So basically what it does is create private throw prod for each one, and at the end it just adds the results together.
It's always like when I do for it means like OMP, and it means doing reduction for the for, right? That's what it means.
Within this for loop, it knows the validity of the for loop, where it starts, where it ends, and so within this for loop, it knows it's supposed to do a reduction on this particular variable, and it knows that for each thread, the J has to be kept private.
Okay, so if for example I wouldn't put here a loop, so what would happen?
If you had no for loop, Probably nothing. Oh, but I mean, if you didn't have this for a loop, we would do the next one, right?
Okay, well, sounds complicated for a compiler, you know, actually.
Yeah. I mean, but there's a specification there. They know what they're trying to do, right? So, but the thing is, yeah, it can be very complicated, right? Oh, sorry, I've gone off. Okay, no worries. So basically, hopefully some of you managed to get that working. Did anyone get a performance number back? Was it better?
Communication time is 0.168.
0.1, right? So before, I think we were on the region of like 7 seconds or something like that. So, right, so the previous wall clock time, we can have a look on my, at least for my run. I did it earlier, so for the blocking run, the communication time in my case was 6 seconds. What did you get with your send receives and your
0.16?
Right, so we had a massive performance improvement when we used the send receives and the barriers. The solution I actually give in the exercises is the non-blocking case, where actually we use non-blocking communication, so not the send receives. I have a feeling that it probably won't even do as well as yours, to be honest. But we can run it anyway. It'll only take a second to run. Okay, we're already there. So let's have a look inside the non-blocking. Done. Yeah, mine was actually worse, right? So I got down to 1.55. I was relatively happy with that. Yours is better probably for a number of different reasons, but basically I can see I still spend a lot of time in my MPI. Of course, that's basically all the program does is do MPI, right? So of course it's going to spend time in there. Look at the difference here, though. My time spent in my peer-to-peer communication has changed dramatically. So basically, it doesn't spend a lot of time waiting anymore. That's effectively what happened. In your case, you should see something similar, I'd say, in your output.
Time spent in MPI 91.
Yeah, and then the peer-to-peer, are they low numbers or high?
High, 44.
Yeah, but okay. In your case, it's a little bit different, right? Because your actual execution time is much less than mine, right?
So
in percentages, it's higher, yeah. Yeah. Okay, that was basically it. I just wanted to bring that kind of stuff to your attention a little bit. So the idea, the advantage potentially of the non-blocking communication is that I could have hid the communication a little bit. When it was doing the non-blocking set, I could have put some extra computational work inside to give the processor something to do while they were waiting for the computation to complete. The problem a little bit with that is that what actually happens depends on the implementation. So in theory, that's what can happen. You can send a message in the background, it happens, and you do something. In reality, the implementations don't necessarily do that very well. So don't spend too much time trying to do these things, because what actually happens depends on the MPI, depends on the implementation. So in theory, it should work. In reality, if it's not supported by the implementation, it's not going to work very well. Okay? It might change a little bit. So the other day they were talking about how, the Mellanox were saying about how they would move particular operations onto the InfiniBand, onto the hardware itself, right? And in that case, you can see how an implementation could be very clever, right? Because then it can really actually do the sending without using the CPU at all. You can actually do the sending in the background. So in the future, this approach could have much more impact. The reality of the current situation is the impact may not be so high, right? So don't spend too much time doing it. It's good to be aware of the idea, but it might not help you so much, right?
But in both cases, the API implementation, if you use the MPI special commands probably be better.
Yeah, if you can, I mean, the special commands like send and receive, like in your case, right, you did better than me, I did the blocking ones, right? But the result of that would depend on the implementation. If I used the Intel MPI instead of OpenMP, maybe the things would be reversed, right? It really depends on what the actual vendor does inside. So, and that's the thing, right? But send and receive in this case is a really good one to use. And of course, you use these things also to avoid deadlocks. In our case, we didn't have a deadlock because the code was correctly written in the first place. But the reality is that we could have easily had, right? If everybody had sent instead of waiting to receive, we would have just had a deadlock because everybody would have been sending. So this call would have, the send receive would have avoided the deadlock as well. And of course, you use them also to avoid waiting until everybody is ready to communicate. You can avoid idle time with these kind of non-blocking sends, and that does work. Yeah, okay. I mean, we've already looked, we don't actually need to do this hands-on because basically we've just talked about exactly what would happen. We get much better performance improvement. The send receive was actually even better. Yeah, if it had more work to do, you could insert it in theory in between the non-blocking send and the corresponding wait, right? But we don't have more work, so we couldn't do that. And that's basically it to this presentation again. All of my presentations, I essentially take them from somebody else's and just shorten them down a little bit, and I molded them for this particular school. This guy, Rolf Rabenseifner, he does really good MPI courses in general, but they're 1 week, 2 weeks long, and it's hard to squeeze that into 20, 30 minutes. So they do put all their stuff online, so if you are interested in doing more parallel programming stuff in general on MPI, it's probably a good place to look. But of course, in general for MPI, it's around for like, I don't know, 20 years or something, so there's loads of material, good material out there. And then, yeah, he has some programs and stuff there. So that's the MPI hands-on. Time for a break, and we'll come back and we'll do the IO.